Hi all, let's see the next topic of Unit 5, design issues in pipelining, or we also call it as the hazards. In today's lecture, we are going to discuss about the definition to hazards or a pipeline hazards and different types of pipeline hazards. And next we go on with one of the type of a pipeline hazard, which is the data hazard with examples. So coming to the introduction, we have already seen the concept of pipelining in the previous lectures. So pipelining implements the concept of parallel processing environment where we can execute multiple instructions simultaneously in the pipeline at different stages of their execution so that the throughput of your system increases. Coming to an issues, there are also certain issues, design issues in pipelining, which are called as a hazards or pipeline hazards. So, what is a pipeline hazard? So, hazard is nothing but it is a situation that causes a pipeline to stall is said to be called as a hazard. Any situation or a condition which makes the pipeline to stall is called a hazard. Say, for example, there are n number of instructions, or say, for example, there are three instructions that are currently executing in the pipeline simultaneously. Any instruction out of them is not able to continue execution in the pipeline during its designated clock cycle, then the particular instruction is said to be stalled. So that situation is said to be called as a hazard situation. So hazard is nothing but it is a problem with the instruction pipeline in the central processing unit that will lead to incorrect results or incorrect computations. So the pipeline hazards are nothing but the situations that prevents the next instruction in the instruction stream from execution during the designated clock cycle, because of which the instruction has to be stalled. Stalled in the sense it has to stop its execution for some amount of time. So that type of situation is called as a hazard situation. So whenever an instruction is stalled, what happens? All the instructions which are present later in the pipeline, which are after this particular stalled instructions, they should also be stalled. So the instructions earlier than the stalled instructions will continue, but no new instructions can be fetched after the stalled instruction. So that type of a situation is said to be called as a pipeline hazard or a hazard situation that occurs in a pipeline. Coming to the types of hazards, there are basically three types of hazards that occurs in a pipeline. One first is the data hazard, structural hazard, or and control or branch, or we also call it as an instruction hazard. So let us see each and every type of a hazard with an example. First, we move on with the first type of a hazard, which is called as a data hazard. So, what is a data hazard? Data hazard is nothing but it is a hazard situation that occurs in a pipeline due to a data dependency situation between the instructions which are being executed simultaneously in the pipeline. So, if there are multiple instructions present in the pipeline, the data hazard situation occurs when they exhibit a dependency between the instructions that are present in the different stages of the pipeline. So, a data hazard is a situation in which the pipeline is stalled because of the data to be operated is delayed for some reason. So, the data which is requested by a particular instruction is not available at the particular point of time which needs to be executed because of some situation. It might be because of any reason, but it is not available at the time expected in the pipeline. We call it as a data hazard situation. For example, if you consider this pipeline, there are five instructions which are present in the pipeline. So we are dividing it into a four segment pipeline where stands for fetch stage, D stands for decode stage, E stands for execute stage, and W stands for write back stage. And between each and every stage of the pipeline, we have intermediate buffers that are present between any two stages in order to accommodate the data. So after the fetch stage is completed, the data is present into the intermediate buffer B1, which is given as an input to the next stage D1. Similarly, we have B2 here, which is used to take the output of the D1 stage and the data is stored into B2. So between each and every stage of your pipeline, an intermediate buffer will be placed. So the instruction I1 is fetched in the first clock cycle, decoded in the second clock cycle, executed in the third clock cycle, and write back in the sense W stands for a write back stage. So here, whatever is the result that has to be written into the destination registers or destination location in the write back stage of your pipeline. So for the instruction I2, the fetch stage takes place in second clock cycle, decode stage takes place in the third clock cycle, and for execution, it is taking more than one clock cycle. Say for example, it is a divide operation or a multiplication operation which is taking 3 clock cycles, 4, 5 and 6. So the write back stage of this particular instruction I2 will not be completed until the end of the sixth clock cycle. So because of which what happened, the decode the I buffer B2 will holds the data of the instruction I2, and it will not release, or it cannot take the data of the next instruction until this execution state of this particular instruction is completed and at the end of the sixth clock cycle and placed into the buffer B3. So because of which the instructions which are present later in the pipeline cannot proceed further, I3, I4 and I5. So the decode stage, the I3 instruction will be fetched in third clock cycle, decoded, but it cannot place it output into the buffer B2 because buffer B2 is still holding the data of instruction I2. So it has to be delayed until seventh clock cycle. So similarly, because of this, the instruction I4, even though the fetch is completed, it cannot be placed into the buffer B1 because the I3 instruction is still holding the buffer B1. So it will also be delayed for the next 2 clock cycle. So because of which the instruction is taking more amount of time to execute, the delay it creates a stalling or delay of the remaining instructions which are present in the pipeline. So it creates a stalling of 2 clock cycles. The instructions I3 and I4 are stalled for 2 clock cycles. So the stage E in the 4 stage pipeline is responsible for arithmetic and logic operations. So consider it is a divide operation which is taking 3 clock cycles. And I2 instruction requires 3 clock cycles from 4 to 6. So in clock cycles 5 and 6, the write back stage must be told to do nothing because it has no data to work with. So it will not perform anything in 5 and 6 because it will get the data only at the end of the sixth clock cycle. Meanwhile, the information in the buffer B2 must remain intact while the execute stage has completed its operation. So this means that the stages 2 and stage 1 are blocked from accepting the new instructions because the information in B1 cannot be overwritten, right? So the steps D4 and F5 must be postponed. Pipeline is stalled for 2 clock cycles, and this leads to a situation called as a pipeline hazard situation. So a data hazard is any condition in which either the source or the destination operands of an instruction are not available at the time expected in the pipeline. So as a result, what happens? Some operation has to be delayed, as a result of which the pipeline stalls. Now let us take an examples of data hazard situations. Consider a program that contains 2 instructions, I1 and I2. And when this program is executed in the pipeline, the execution of I2 can begin before the execution of I1 is completed. Okay, so let us see. Consider there are 2 operations, 3 plus A will give you the result A, and B we are performing 4 into A. The initial value of A is 5. So when you perform these operations in the order, the result of B will be 32 because 3 plus 5 gives you a value of 8. 4 into 8, it will give you the updated value of B as 32. But if you consider if this instruction I2 is computed before the instruction I1, then what the I2 will do, it will take the original value of A and makes it as 4 into 5, right? It leads to incorrect results. And remember, whenever we execute the instructions in the pipeline, we have to ensure that the output of a sequential execution must be equal to the output of a parallel execution. So if you execute these instructions one after another, it will give you output result of B as 32. But if they are executed if in the pipeline, if I2 is executed before I1, you will get an incorrect result of 20. So we have to, when you are executing the instructions in a pipeline, we have to ensure that the result of the sequential execution must be equal to the result of your pipelined execution. So if these two operations are performed in the program, the instructions must be executed one after the other, because the data that is used in the second instruction depends upon the result of your first instruction. So when these two operations depends on one another, they must be performed sequentially in the correct order. So it means that if the instructions are independent instructions, then you can execute out of order. But when you are using the instructions which are dependent on one another, you have to ensure that the output of a sequential execution must be equal to the output of your pipelined execution. Now, if you consider this example, 5 into C and B is 20 plus C. So, if you look at the values of A and B, they are using the value of C, but both are independent instruction. The output of I2 is not dependent upon I1, where I1 is not dependent upon I2. So, they can be executed simultaneously in the pipeline, or they can be executed out of order. There is no problem because they are independent instructions. The result of one instruction doesn't affect the result of another instruction. So there is no data dependency situation in this particular example. Now let us see one more example of a data hazard situation. So here we have first instruction is a multiplication, where we are going to perform a multiplication on the contents of two registers R2, R3, and the result is stored into R4. Next, coming to addition, we are going to perform an addition operation on the contents of R5 and R4, and the result is placed into R6. So if you look at this, the destination operand R4 of the first instruction acts as a source operand for the next add instruction. So there is a dependency of instruction I2 on the result of the previous instruction I1. So if you look at when these two instructions are executed simultaneously in the pipeline, consider the I1 is a multiplication. It fetches in the clock cycle 1, decodes in the clock cycle 2, executes in the clock cycle 1, the 3, and write back operation is performed in the clock cycle 4. And similarly, if you consider I2 in clock cycle 2 and decoded in the clock cycle 3. But in the decode stage, we have to know what are the source operands and get the source operands. But the source operand R4 will not be available until the write back stage of this particular instruction multiplication is completed at the end of the fourth clock cycle. So the decoding step of the instruction I2 has to be delayed until the fifth clock cycle. So in the fifth clock cycle, the decoding will be done, and then the execute and the write back stages will happen. So here, because of this particular instruction is stalled for one clock cycle, the remaining instructions in the pipeline are also delayed. So the instruction I3 will be fetched because it cannot proceed with the decode. The decode unit is busy doing this instruction I2. So it has to be delayed until the sixth clock cycle. So pipeline is stalled because of a dependency between D2 and W1. So this is called as a data dependency situation. If you consider one more example, the first instruction is an add which uses R1, R2, R3. So here R1 is the destination register and R2 and R3 are your source registers. So if you look at the remaining instructions, the R1, which is the destination register of an add in first instruction, it is used as a source operand in all the remaining instructions. Sub, here we are using R1 and you are using R1 as a source, or we are using R1 XOR you are using R1. So the add instruction writes the value of R1 in the WB stage, and the sub instruction read the value during the decode stage. So there is a problem called as a data hazard situation. Because of the data dependency situation, the pipeline has to be stalled. So this is one of an example, other example of a data hazard situation. Next, coming to the types of data hazards. So there are three situations in which a data hazard may occur in the pipeline, or a data dependency situation occur between the instructions that are executed in the pipeline. The first type of a data hazard is a read after write hazard, or we also call it as a RAW hazard, or true dependency or flow dependency. The second type of a data hazard is a write after read, which is called as WAR hazard, or we call it as a false dependency or anti-dependency. And the third type of a hazard is a write after write hazard, or we call it as an output dependency. So these are the three types of a data hazard situations that may occur in a pipeline. Let's see each one in detail. The first type of a data hazard is a read after write hazard. So if we consider two instructions I and J, with I occurring before J, in the order I and J are instructions executed according to the program order. So in case of a read after write data hazard, this type of hazard situation occurs when J tries to read a source before I writes it. So a read after write data hazard refers to a situation where an instruction refers to a result that has not yet been calculated or retrieved. So say for example, we have instruction I1 where R1 plus R3, and the result is written into R2, where the instruction we have another instruction I2 where this particular destination of register is acting as a source operand for the next instruction R2 plus R3, and the result is written into the R4. So the first instruction is calculating the value to be saved in the register 2, and the second instruction is going to make use of this R2 to compute a result for the register 4. So however, in a pipeline, when we fetch the operands for the second operation, the result from the first will not be available, because it will be available only after the write back stage of this particular instruction is completed. So there is a data dependency with the instruction I2, as it is depend on the completion of the previous instruction I1. So this type of a situation is said to be called as a read after write. Read after write. So why we call it as a read after write hazard is the instruction I2 has to perform a read operation of this particular register R2 as its source operand only after the write back stage, or write back stage of this particular instruction I1 is completed, so that the value of R2 will be available. So you have to perform a read of operation of instruction I2 after the write operation of instruction I1 has been completed. That is the reason we call it as a read after write data hazard situation. The next type of a hazard situation is a write after read data hazard. So when J tries to write a destination before it is read by I. So say for example, for both the instructions I1 and I2, a write after read data hazard represents a problem with respect to the concurrent execution. So if you look at these two instructions I1 and I2, the first instruction is going to perform an addition of the contents of R1 and R3, and it is stored into R4. The second instruction I2 is performing the addition on the contents of R1 and R2, and it is written into R3. So say for example, because of concurrent execution, the instruction I2 completes before I1. So if you look at this, R3 is a destination register here, where it also acts as a source operand in this particular I1 instruction. Say if the problem here is when I2 completes its execution before I1. So what happens at that point of time, there is a possibility that the write back stage of I2 will take place before I1 reads this particular value. So we call it as a write after read situation. So if it is in a situation, there is a chance that I2 may be completed before I1. We must ensure that we should not store the result of register 3 before I1 had a chance to fetch the operand. So that is the reason we call it as a write after read. Right? We have to perform a write operation of instruction I2 only after the read operation of instruction I1 has been completed. That is we call this is called as a write after read data hazard situation. The third type of a hazard situation, data hazard, is a write after write data hazard. So in this case, for both the instructions I1 and I2 or I and J, there is only one destination register. So a write after write data hazard may occur in case of a concurrent execution. So this also occurs in case of a concurrent execution where both the instructions use the same register as the destination registers. So in this case, so here the instruction I1 performs an addition of the contents of two registers R1 and R2 and the result is written into R2. And similarly I2 will perform the addition of the contents R4 and R7 and the result is written into R2. In both the cases R2 is the destination register. And consider a situation in which the I2 completes its execution before I1. In that case, we have to make sure that we have to delay the write back stage of the instruction I2 until the write back of I1 is completed. Because as we know, the main rule is of pipelining is the result of the pipeline execution must be equal to the result of a sequential execution. So only when we perform the write back stage of this I2 after I1, then only we get the correct result. Or else it leads to incorrect results. So we must delay the write back of I2. Even though the I2 is completed its execution, we have to delay the write back stage of I2 until the write back stage of I1 is completed. So that is the reason we call it as a write after write. So this is called as a write after write data hazard. If all these type of situations occurs in a pipeline, we call them as a data hazard situation. It can be either a read after write or a write after read or a write after write. All these leads to a data hazard situation, which is nothing but the data dependency situation occurs between the instructions which are executed simultaneously in the pipeline. Thank you.